Hey, can you all hear me? Let's see. I think you should be able to hear me. I hope. Okay, we'll be starting in 2 minutes here, I guess. About. Hmm. Okay, let's see. We're trying to figure out if it's my first time setting this up, so we'll see if I can actually hear things here. Everything's audible. Mm-hmm. Um, Great. Hi, can you hear me? We'll see. There's a little bit of a delay here, so but if you can post in the chat if you can hear me. Yeah, hopefully this will work. I just kind of started getting all this set up, so but I'm hoping we'll have a good session and we'll just oh, nice. Okay. So you can hear me. Great. All right, let's get started. So I'm thinking today we'll create something, just a little simple game, something called Refraction Racer, where the basic premise is, asteroids, the game, where you um, fly around a spaceship, and I want that kind of mechanic, but when you pass through various uh, areas, then you get sort of refraction effect, and maybe we'll also multiply the velocity that we're going, so it becomes hard to steer when you go through these areas, but you basically can go extra fast. Um, so if that sounds cool, we'll get started. And kind of the basic premise here is we'll be developing a basically a simple vector and physics library. And simple, yes. We'll do a little library where we'll have some vector functions and some, intersection things and some, some physics, I guess, in there as well. And we'll just try to quickly put this all together. And in the end, we'll have this org mode document that I'll just post on GitHub. And so you can reference it later. And also all the code that we write here will be out there as well. So everything I'll do will be in here, and then we will also basically have it in the code. And then I think you can probably see the Dragon Ruby output over here. So let's just, we'll just kind of print something or display something here just to sort of have something on the screen. And then width 50, height 50, and that should solids. Oh, there we go. Yep, so we have a little screen there. Okay? That sounds all right. We'll get started. Okay, so with our little game here, I think the first thing that we want to do is have our little spaceship that flies around. And for that, for now, I guess we'll just draw a little thing out of lines. So draw spaceship or display spaceship. And actually, we'll draw this to a render target. So our spaceship, I'm thinking, will just be something like we have our 0 and 0, or our, let's see, our 0 is our origin here. So this is the bottom left of our render target. And this is our x direction, and we have our y direction here. So I'm just going to draw something where we have a point at 0, 0, and a point at, why don't we say 1, 1.5, and we'll have another point at 2, 0, and just combining these lines, and then we'll just add in another one at, let's see, yes, render spaceship. That's probably what we want to call it. We'll rename it in a sec. 1, maybe 0.5, and that'll be our little spaceship. Something like that. Wow, okay, there we go. So that is what we're trying to do. Okay, so we'll do render target, and we'll call this spaceship. And we'll render. We'll do this out of lines. And actually, does anyone know if, can I do something like that? Maybe. Usually I just do this. So we'll just quickly put something together here. Y2, that, so that's our first line here. And then we'll duplicate that. And actually, won't I shift this over? X2 is 2, Y2 is 0. So now it's this part here. And paste that once more. Yank 3. Yeah, right? It's good enough. That's all I'm going here for here, is just everything just has to be good enough for the purposes of my low quality spaceship. I'm not really going for performance on any of this. Oh yeah, that's the other big thing, is the main focus of these videos is more to make it easy to understand and less about performance. Although we might be able to get into some of that later on. But for today, we're just going to be focused entirely on just getting something. Okay, so let's try to draw the spaceship here. Render spaceship. And of course, we don't actually draw the thing, so we'll have a little display function here. Def display, args, And we'll do args.render. Oh, you know what? I'm using 1 for all these. Let me make this a little bit bigger. It's a little bit too small. We'll multiply all these by... Yeah. Levi, I figure that's you, right? Oh, let's see, did I do this correctly? No, this should be 20, and this will be 30. We'll have this be 40 and 0. Realized I had not multiplied any of these things, so it's going to be tiny. Just, of course, there are probably better ways of doing this. So if you know how to do it better, then let me know. Okay, so now let's actually display this. Well, I was kind of keeping things as render for render targets, and then display for anything in real time, or that we do every tick. So this is only just the one at state dot tick count is 0. That's the only time we'll be doing that, and then otherwise we'll be doing this display, which doesn't actually do anything yet. So we'll do path, spaceship, and we'll put this for now. Let's put this somewhere kind of in the middle. It's a little bit closer to the center here. And we'll make this basically the same size as this. So this should be 40 by... Should be 40 by 40, right? No? Why did I make this? Oh, yeah, that I guess is correct. This scaling is totally wrong, so we'll probably adjust this a little bit later. I think this was... Oh, yeah. Go design your game. But yeah, I should be able to do that. You're right. Should be able to just do something like this, right? See, these are the things that I assumed you could do and just never bothered. Figure that should be legal. And of course, still complaining, but that's not that surprising. Source X, we'll have it be 0. Source Y is 0. Yeah. And then source width, of course, is our 40, and source height is 30, which, again, this will look kind of ugly. Sprite, outputs. And there's a poor quality spaceship that doesn't really look like one. Why does it not look like one? Let's see, I'm missing a line here, or... Oh, this right here. This should be 10, and then it will be a little bit more, and then I'm just going to actually put in gtk dot reset up here so that we redraw. Okay, so we have something there. Doesn't exactly look great, but actually I think we want to shrink this down a little bit anyway, so we'll just kind of bump this down to 20, and we'll do... Yeah, 30 is fine for now. We'll worry about the rendering of this a little bit. Yeah, kind of like this, right? So, yeah. Oh, can I? Well, that... I think I still... It looks like I need it. Need the sources. Or at least I need some of the sources. I'm not sure about the width and the height. I might not need those. No, looks like I need those too. So, yeah. Render target. Obviously, we would want to do something a little bit cleaner later on. But we can do that after we've done the intersection code. So why don't we first try to actually drive this thing around? So this right now just is rendered in a single location, but rather we will want to set up some state for this. So we'll just create a little thing here. Source then spans for the entire sprite. I see. Yeah, I'm not sure if, because when I commented this stuff out, I mean, I tried a couple combinations I think you saw, and it didn't seem to render, so I just tend to add it in manually, but of course I'm still new to Dragon Ruby, so yeah, any tips on any of this would be helpful. Okay, so setup. Let's see. So we want to add some state, and we want some position for our spaceship. Dot position. We'll just call this pause to simplify it. And now let's actually start doing a little bit of our vector library, right? So our position can be, as kind of obvious, can be some x and y position. And so we're going to start it at our 500 and 300 here, and we'll just change this over to rx.state.spaceship.position, say 1, rx.state.spaceship.position. And actually, right now I'm using just the right now I'm just using the array instead of a vector. So we'll actually switch that out, since I figure that will be easier for us to deal with. So we'll call this setup args. And now we have our spaceship again. And if we change this position here, then of course it moves to the new position, right? And if we wanted to basically just have it move around via the mouse, follow the mouse around, then we would just do something like dot position equals args.state or inputs.mouse.x and args.inputs.mouse.y, and then now we have our sprite following around our mouse. Okay, so okay. Yeah, everything will be available as a video, and also there will be an org mode file which talks about pretty much everything here. So hopefully some of it will be useful. Okay, let's start building up our vector library. So I'm going to be using this down here. This is org mode. So we'll just kind of stick everything in here, and then we'll kind of copy and paste what we have up here so that we have both the document and this up here. So this is actually pretty cool because it's kind of like Jupyter Notebook, where I can write, for example, hello world. And then if I hit control, well, that was not quite, oh yeah, this is more, yeah, so you can see it like returns things. And we can also do like outputs and things like that. And it also has fancy rendering for like arrays. So we can do, right? Yeah, it's all Emacs. We're going to be running entirely 100% Emacs here. So except for this thing, my paint, which is fantastic, by the way, if you haven't used it. So okay, vector library. Let's start by just defining a class here. And we'll just make this, we'll explicitly call it vec2 because at some point we'll also do 3D. Not today, but, and we'll just, here. Okay. So our class vec2 will have a initialize, and I don't necessarily recommend you do things this way, just because it's a lot easier to understand, but there are definitely some performance impacts as a result of doing this if you're doing, if you're dealing with many, many vectors. So, yeah, well, yeah. So now we'll also just add in a few. Yeah, we'll just call it v for vector. And we'll just say if v dot is a vec2, then we can just create a new one for now. We'll do at x plus dot new at x plus v dot x at y plus v dot y, and then otherwise we'll return at x plus, and again, we're not going for any performance related things here, and if you want better performance, you probably do something that mutates the thing instead. So we'll just copy this over here. And so essentially what we're doing here is just constructing the basic parts of our new vector library, which I'll just kind of send s plus minus g, and then we'll just do that again. So I'm thinking actually for multiplication, by default, multiplication will be a probably element-wise multiplication. Not that that's most commonly used, but it just simplifies things a little bit to do it that way. Just, I like to be explicit about the different types of multiplications that we use. So element-wise, it's kind of the default in a way. I guess you could also have it be the dot product, which, speaking of, we should probably put together a dot product as well. So everyone's familiar with dot product? Let me actually kind of bring up, well, okay, before we do dot product, let's actually just put this in, and we have the simple math. Obviously, this doesn't do anything. Class definition and body. Well, I did something dumb here. What did I do? Something stupid. Class definition method body. Vec is a vec. Okay, we'll just stick this in Dragon Ruby and see what happens. Oh, yeah, we also need the attribute accessor. Well, I'm making mistakes. We will call this, so I think just something like that. X, Y, this isn't right. No, that's still not right. Let me actually check my, yeah, we'll do cross product too, and I'll explain a little bit of the differences there, since both of those are really useful. But basically, cross product, it's a scalar on the sine, and the dot product is a scalar on the cosine. So that lets you do a lot of useful things. Or other way, dot product is sine and cross product is cosine between the two angles. So, for example, with the dot product, if you get a negative value, then you know that the angle is greater than 90, or if it's less than, or if it's a positive number, then you know that it's pointed the same direction. So we'll cover things like that. Yes. Attribute. Oh, I am missing. There we go. I spelt it wrong. I was missing an S, I think. Okay, great. That looks better. Okay, so we have this, and that's fine. I figure this will not class definition method body. Well, we won't worry about that right now. I guess we'll go back to the Ruby file, and we'll just kind of drop this in, and we'll probably get an error. And then we'll figure it out from there. Okay, no error, so I guess it's fine. And let's go back to our code here. So we have all these things, and we'll instead set this to be a vector. Okay, so we'll just have this be, 400 by 400 is a fine starting point. And of course, it will complain initially. So we'll do .x and .y, and we'll also want to subtract off our width and height here. Minus 20 over 2. And now we have it in the correct position. Yeah, so that looks correct. Okay, great. So let's do some basic forces first. So right now we have a spaceship, and what we're going to do is we're going to give it a mass, and basically, as it travels through space, we want it to have natural accelerations and basically something where we have a propulsion system of some sort, and that's giving us constant force. And that's how we'll drive around our spaceship. And then also we will potentially add in some friction. So I know we're supposed to be maybe in space or maybe in some other area, but we're going to pretend that we're not in a vacuum, although we'll get there in a bit. Actually, I don't know if we want to do that. So we'll just have like a update. Why looks wrong? Probably. Yeah, you're right. This should be 30. Okay. Catch. Yes. That's catch. Okay. Great. So we'll do a little update state. And for this, I actually like to typically use real world units. So I actually define, I know Amir's gonna complain about this, but I usually set up a DT so that I can get real physics instead of something which is kind of, fake, or just pixel space. So rather, we'll be working with real world units here. Okay, so step one, of course, is we're going to treat our spaceship as a point mass. So we need to actually add in a mass for this. And we'll just say, for the sake of this, our, spaceship is 5 kilograms, which is a tiny value, doesn't really do much. That's fine. We'll just leave it as is. And then this also has a velocity. Velocity, call it vel, and we'll have it go at 0 initially. Right? Yeah, the dt. So we have a spaceship velocity, and we'll also have an input here. We'll just put this down here, process inputs, args, and we'll do update state on args as well. And then we'll just apply a force. And actually, we're going to just keep this as scalar here. And the reason we're going to keep it as scalar is whichever direction the spaceship is facing, we'll use as the direction that this force is applied. And that actually reminds me, we also need an orientation. Orientation. So orient. And for the most part, I'll be working in radians here, but for the actual orientation, I'm going to keep it as a vector. So initially we'll have it be, 0, 1, and this we'll try to keep as a unit vector. So basically a unit vector has a magnitude of 1. So something like, anything along a unit circle is valid. So we have a vector, something like this, and the distance here has to be 1, right? So basically anything along a circle with, wow, that is a bad circle, with a radius of 1 is going to be our unit vector. Yes, there will be amazing drifts, and also it's going to be trippy, like really trippy. driving this thing around, and it's going to be terrible as far as gameplay goes, but that's okay. Since I'm not really here for that, I'm just here to have fun. So, okay, so we have our velocity vector, and that's pretty simple. So right now we're just doing 0 and 0, and that's actually different from our orientation vector because we can be facing any direction, right? So would it be better if we... You know what, why don't we actually keep this as a angle? So we'll have this in radians. Args dot state dot spaceship dot. So I'm gonna say if args dot. So basically the way we drive this around is left will be rotate to the left, right will be rotate to the right, up will be go forward, and I guess backwards won't do anything. Maybe we'll add a drift mode later, but for now, that's all. Yeah, that's all we'll be doing. So if args.inputs.keyboard dot key down. No, not key down. I think we can just do left arrow. There's actually like a directional thing, I think, which we can take a look at in the docs. Directional. Oh, I guess we just use... Let's see, org mode this. Okay, so left. Yeah, directional. Let's take a look here. So directional vector, yeah. Left, right. Okay, cool. Yep. Yeah, so this right here is what we want. And there's also up, down. Left, right. If... So I guess we'll just be adding a multiplication here. So we'll have our args.state.spaceship.orient plus equals args.inputs.keyboard.left right. And actually we can get rid of this. And then we have some scalar. So we can have our... And we're not going to deal with angular momentum in this video, but we'll worry about that in some other one. So we also have our angular vel, max angular vel, which is our maximum rotational velocity here. So we'll actually do math over pi over, why don't we say over 6 for now, and actually don't what? I'm sorry, the chat is pretty delayed here, so we'll just do something like that. And then our angle here is directly from args.state.spaceship.orient times math over pi over, or no, other way, okay. Over, or times 180 over math pi. And now we should be able to, whoa, it drives way too fast. Okay, and this should be minus equals since it looked like it was going the wrong way. We'll do some small value here. Well, still too fast. Okay. We'll go with... Yeah, so that looks a little bit more reasonable. I think it's rotating around the center, so that's good at least. What's not great? Yeah, I don't know. I'm not sure. I'll need to... It's pretty delayed, I think, so I have no idea what your not great is towards, but let me know, and I will try to do what I can. Assuming you're not referring to the lag, which I think that's probably something that people run into pretty often, so it's actually possible it's in the OBS settings, duration, scene transition. You know, I kind of looked into this a little bit, and streaming, yes, the streaming is pretty, it's surprisingly complicated to get working correctly. Okay, so anyway, we'll also add, and this is, I don't love this because the input should be entirely separate from the state of the I was going to say robot, the vehicle itself. But we can just kind of stick things in here for now. If rx.state, or actually, you know what? I think, let me actually check something here. If I type in rx.state.spaceship.force equals rx.state.spaceship. Let's see, or no, rx.inputs.keyboard.up. Then presumably this will give me a 1 or a... Oh no, this does not return false, right? It just gives true. So we'll just put this in a ternary. And we'll say rx.state.spaceship.maxForce equals, and we'll just put in some arbitrary value for now. We'll see how that goes. Spaceship.maxForce, and obviously this is kind of hard to read. So we'll kind of bump this down here. Maybe that's a little bit better. And right now we're not doing anything with this. So now we will actually compute the physics here. So what we're doing here is we have our vehicle, and we want to apply force to it. So we want to first of all apply it in the direction that we're facing. So for that, we need to create a vector. And this vector will be based on the cosine and the sine of our orientation. And, you know, because that gives us, so the cosine, so if we have some theta here, then the distance to here, we have our cosine, this is our cosine, and, or, this is our sine here, and this is our cosine, right? And so by doing that, we can multiply that by whatever force magnitude we have, and then we'll get a vector that has that amount of force in that direction. So we'll take args.inputs or args.state.spaceship.orient, and we'll take the orientation vector. So I guess we'll call this, orientation equals vec.new, and we'll just apply a cosine to this and a sine there, and then our thing crashes because I called this vec instead of vec2, and now it will not crash. Okay, that's good. So orientation, so we have our current orientation, and that's fine. And why don't we actually, should we visualize this? Maybe we will, just kind of to shoot the point across here. It's possible I actually, well, because right now we actually have something confusing here, because we have our vehicle, our sprite is rendered this way, but cosine, of course, goes starting that way. So initially, when we have an orientation of 0, it's actually going to be facing the wrong way here. The easiest way to solve this is simply by setting the sprite to be facing the side instead. So maybe that's what we'll do. I think I just need to flip all these, and then it should be okay. 0, 40, 10, 20. I know there's definitely an Emaxian way to do this. I've been using Emacs for I don't know how many years at this point, but there are definitely things that I just don't do as I'm supposed to. Let's see, there was an error somewhere. Syntax error, line 88, expected. And of course, the problem with these things is that they're never, yes, this line here. Okay, and then we had the width and the height here incorrect. Source, this should be 30, 40, and then we'll just make this 30 and 20. And now we have our spaceship again. Again, poorly rendered. We'll do a clean render later. Let's see. Wow. These things go quickly. The time has... I did not realize it was already 40 minutes in. Okay, we'll speed it up a little bit. So, now let's actually get into some physics. Okay, so we have this facing this way, and we'll first take in apply the force here. So we have our mass, and so as you probably know, F equals ma, right? So that's force equals mass times acceleration. Now, if we take this, we can create this kind of relationship where force over mass is equal to acceleration. And then, of course, from this, we can say velocity times alpha times dt, or velocity equals the acceleration times dt, to give us our velocity vector from our acceleration. And then, of course, then we can also take the position from taking the sum of this. So it's basically we're integrating, but because we're doing this discretely, we can just multiply and add. So this is kind of assuming starting from 0, but it ends up looking something like this, right? So that's how we'll just add this into our equation here. I set out do this as a library. We will, I guess, make the library later. So so our current acceleration for our ship is args.state.spaceship.force over args.state.spaceship.mass. And then from there, we can take our velocity, and so this is basically the velocity computed from this. And rather, what we want to probably be doing here is adding the velocity to our current velocity. So that's what we'll be doing here. So args.state.spaceship.velocity plus equals or this is, let's see, we have the force over mass, and this is our just magnitude for the acceleration. So we do need to put this in a vector. So this is our magnitude, and our full thing here looks like this times, or well, actually, orientation times acceleration magnitude. And then when we add this to our spaceship vector, we'll have our dt here. Then that gives us our current velocity. And note that we're adding this to whatever our previous velocity was. And then we will then add our new velocity, or sort of the position, the integral of this to the position. And that should give us something. Probably won't give us what we want. Oh, right. I don't have... It's driving real slow. Okay. So obviously the force that I applied was not good enough. But we at least have motion here. Let me bump this up a ton. And now we have... Okay, no, still too slow. Okay, we'll multiply this by 5. Okay, there we go. So now we have a spaceship that flies around using just basic forces. And we talked a little bit about basically forces, accelerations, velocities, and how that all comes together. Okay, so that's cool. Now from here, why don't we do something more exciting? We'll do intersections next. So intersections, there are a few different ways you can approach it. I'll just kind of leave this flying here. Can you even see this? I mean, like, must be kind of small. Maybe I'll like add a cube to this just to make it easier to see. Oh, I don't know why that was unhappy there. args.render target, spaceship, and we'll just add a solid that just... Yeah, can you see that? I don't know if you know, it's kind of hard to see, right? Just make this 15 and we'll make this, or we'll make this 10 and we'll make this one in the y direction 10. A width of... yes, of course. Yes, intersections will be good. And then we'll just have, we'll kind of talk a little bit about the multiple approaches that we can take. And then we'll implement it, and then we'll have collisions as well. And then refractions as a result of that. And I'm hoping we can get through that pretty quickly, but we'll see. And if you get bored of it, let me know, and we'll move on, or we can stop the stream at any point. I don't want this to go too long, but okay, now you can at least see the spaceship. Cool. You can see the code, but can you see the... yes, because we didn't do wraparound, which we might not do wraparound. Okay, cool. But we at least have a spaceship that drives around, right? Okay, so we've done our velocity. Now let's do intersections. So essentially what I want is when the spaceship goes through some surface, I want it to refract. So I want it to like just change direction. So that's kind of my goal here. I don't know if it'll be fun, but it'll be kind of cool. So what we'll do is, let's see. So the step 1 for this is to find this intersection point, right? So we want to find this. Now, yeah, the solid I figured would help quite a bit. So of course now it's gone again, so we can't see it, but we can fix that, but not important. I kind of want to just do display, just, or no, I guess I just want to do modulo 1280, and we'll just do a modulo 1280 or 720 here. And now, presumably, if we spaceship this thing around, then it should wrap around. Yep, good. We can keep going faster and faster. Okay, great. Now we have a distracting spaceship flying through. That's actually too much. Stop it. Okay. Okay, intersections. So what we're going to basically do here is, in order to compute the intersection, at every step, we have our spaceship location, and then we have any line that we want to compare with, and we have some dt. So at each tick, we have some distance that we travel. And so essentially what we're going to be looking for is the intersection point between this line and whatever polygon that we're hitting. So in order to do this, we have two different vectors that we're comparing. So we have this, which has, I think we're going to call this qx and qv, and this is qx plus some rx, qy plus ry. And I think you probably will recognize this from that same Stack Overflow that you were referencing, Levi, for but so there's kind of the vector approach, or we can also take the traditional approach of we have two lines with some angle and some, some basically equation that we can line equation that we can use to compare. There are a couple issues with this approach. The first thing is if we have something like that, it's undefined and will give you infinity for result. Also, if you try to compare something that's vertical with anything, then this breaks because there's divide by zero, right? Okay, yeah, so we'll go through that. I'll explain it. So alternatively, we can use a vector-based approach, which there's an awesome Stack Overflow, which is right here. So what this does, we have our p plus r. I'm sorry, this was backwards, wasn't it? We'll fix that in a sec. And we're essentially looking for some intersection. And so why don't we go through this and try to understand it, okay? So why don't we start with sort of the very basic part of this. Okay, so the goal here is to find some t and some u, which are scalars, to find the intersection point. So what that means is we have our, this is exactly the same thing that I was referencing. So we have some p, some point p, and this vector from here to here is r, right? And that's why this line is defined as p plus r. And so this position can be defined as p plus r, right? And the same thing can happen here with our q and s, which we'll define as this thing. The q plus s here. Okay, so we're on the same page there. Now, what this bit here is saying is that we can have a scalar on r and a scalar on s that shift the magnitude of this. So essentially, if we just look at r here, right, and we have r, let's say we have this be at position 1, 1, and then we decide, okay, we'll have a scalar on that, which we'll call t, and where t equals 2, so t times r is some vector that's pointed in the same direction. So it's now t times 1 and t times 1 for that position. So we're just multiplying whatever original vector that we have by some scalar. And so what that means is that we can actually kind of shrink this guy, so that instead of it being this length, we are now looking at this length to the point where it intersects. And the same thing with the q, where instead of looking at the whole length, we can scale this, scale s so that it hits, okay. Is that better? Yeah, I was a little bit worried about that and about Dragon Ruby obstructing the view. And then I didn't do a good job about fixing it. Okay. Maybe now it's a little bit easier to see. So we have, okay, let's go back. So we have, let me make sure that, yeah, okay, now I have the window up so I can see exactly what you're seeing. Okay. Now we have our R. So we're just looking at the difference from this point to, or this point to this point, right? And that's defined as R. And we can have a scalar multiplied by R, which just changes the position. Has to be above the gain slider. I have no idea what you're referring to, but that's okay. Or maybe it's not. You should let me know. But we can multiply this by some scalar so that we get some t times r, which just has coordinates t times the original rx, comma t times the r times y, right? So then we can kind of adjust this so that this scales all the way down to the point in which it would intersect. And the same thing on the other side. We can scale it. We can scale this q so that it intersects with the point of intersection. And that's what this is saying. So when we talk about p plus t of r equals q plus u of s, these two are our scalars to try to get to this point of intersection. And so those are the variables that we're trying to find. Now, when we actually kind of go down here a little bit, so effectively what we're doing is just some basic, let's see, gain setting on the right side. You can estimate whether you can see it if you're driving. We can see what you draw by seeing if it is above it. Are you referring to I'm using OBS. I don't know if you're referring to the same thing that I am, but for now I can also just kind of shrink this guy. And then you can see more. Or actually, you know what? No, I think I can just hide it. It should be even better. Yeah, okay, that's cool. Okay, so now essentially what we're doing here is we're solving for those t and u values. And that's all that's happening here. They multiply by the cross, basically to eliminate this cross on this side here. And then gain. Oh. Is it too small? I don't know what you're... I can certainly make it bigger. Okay, well, I hope that's visible. Is the drawing, are the drawings viewable, visible? Yeah, it's okay. All right, great. Okay, so so all we're doing here, we're just eliminating the variables here so that then we can pull this out and then we can divide, and that gives us our t. And there's plenty of literature kind of explaining these bits, but essentially what we end up with here are we have these two outputs, right? And so we've solved now for our t and our u values, which if we have these two things, then we know what we need to multiply each of these two to get to this point here. Now, they list 4 cases here, right? So r cross s equals 0, and if r cross s equals 0 and q minus p cross r are 0, then the two lines are collinear. What does that mean? Well, I think earlier, just at the start of the video, I mentioned that cross products are, cross products help us get the sign value, and dot products give us a scalar on the cosine, right? So I think what it was v1, the magnitude of v1 cross magnitude or times magnitude of v2 times cosine of theta is the dot product, and the which I'll write as dot v2. Does it sound right? I think that's right. Let's actually take a quick look. Dot product. Right, so we have our dot product, which is, I always kind of get these mixed up. So, yep, so you just take the magnitude of both of them times the cosine, and then the cross product is the same thing, but with a sign instead. So we'll take a look at that. Cross product, which gives us the sign. And then this actually also has a direction, which is a normal direction in, so this is a unit vector here, which gives us the direction, the normal vector between the two, perpendicular between the two vectors. So this gives us something which we can use to find like a normal of a face or things like that if we're dealing with 3D, or like rotation direction. So we have this is our dot product, v1 cross v2 is equal to v1 times v2 times sine of theta, right? And so this is useful because one property of these, as you probably know, with our circle, cosine gives us our x position here. So this is our cosine, and this is our sine over here, right? And so if our sine is 0, then that means it's along here, right? Which I think was what this algorithm says. So if r cross s equals 0, so if they're pointed in the same direction, if the angle between the two is 0, so yeah, this theta is the angle between the two vectors in both cases. So if it's 0, then the cross product, which is the sine, will give us a 0. And that's true for this part, or if it were over here. So it works for 0 degrees or 180 degrees, which is why we choose the cross product instead of checking to see if the dot product is 1 or -1, because we can do it in one operation there. So this is actually equivalent to checking to see if r dot s equals 1 or -1. Or I guess taking the absolute value of r dot s and checking to see if that's 1. Now, q minus p, so r cross s, so we're checking to see if r and s are facing the same direction, right? If the angle between them is 0. And then we're also checking to see if q and p are 0. Cross product of that is 0. And that also gives us, so that's actually from the origin point, we're saying, okay, q and p, and we're looking at this angle here. So if that's 0, we're in a situation where it's kind of like that, right? So if all these are collinear, then we have something where, or if these are all 0, then we have something where it's collinear, which means the Q and, it might look something like this, where they all line up as a line. And therefore, we can define that as either infinite intersections or no intersection, or, whatever else you want to call it. Now, let's look at case 2, which is R cross S equals 0 and Q minus P cross R is not 0. Then these lines are parallel and non-intersecting. So let's take a look at what that means. So we already talked about what happens if R cross S is 0, then that means that they're facing the same directions. These vectors are parallel, right? So this is our Q, our R, and this is our S. But if our Q and P is, if our Q minus P cross R is not 0, then we end up having, essentially basically it means that these two are in different positions here. So then we end up having two lines that are parallel. And then kind of in this last case here, or third case, we're looking at if R cross S it does not equal 0 and T is greater than 1, or greater than 0 and less than 1, and U is greater than 0 and less than 1, what we're checking for there is if, so 1 is the length that we have from Q, 1 times S would give us the current length that we have. 0 times S would give us just the point Q. So anything in between those two would be within this span here. And anything within this area here would give us, or anything where R is between 0 and 1 would give us the span here. So we just want to bound U and, or S and, U and T to between 0 and 1. Does that make sense? And then otherwise, the final condition is they intersect, or they're not parallel, but they do not intersect, which basically means our point of intersection is somewhere out here. So if we just want to compare between a line and a line segment, so something which goes off to infinity and a vector here, which we define kind of by two things, then in this case, we would actually have, for example, if this is our P and this is our R, or P plus R, and this is our Q, and this is our Q plus S. I'm actually going to make this a touch smaller here. Then what we're looking for here is any case where, we're looking at this equation here, any case where U is less than 1 and greater than 0, but T can be any value and it would still be an intersection here. And if you wanted to just say, oh, instead, I only want to look at points this way, then you just set a lower bound. So that way we can kind of use this equation for all sorts of different things, different types of intersections, and we have like the bounds of it defined as well. So we can look at various combinations. That lets us do quite a bit. So let's quickly implement this. I know we've been going for a while now. But let's see. So we'll have our little vector here, and we'll just do compute intersection intersect, and we'll have Q1, Q2, or we'll have this Q, and then we'll just keep the same terminology here. So P, and actually let me bring this guy over here. We'll just implement this as is. So what we want here is P, Let's see. So we're looking at P, comma R, and Q, comma S. And so these are, our vector points. Did that make any sense? If not, if you clarify which parts didn't make sense, I can try to go over some of that again. Since I know some of these are a little bit tricky to understand, but basically what we're doing is we're just kind of scaling these two lines and trying to find where they intersect by moving them. Okay, so we'll first compute this. So we'll do Q minus P, and then we'll do a cross, which we haven't implemented yet. And we'll do S over R dot cross on S. Now, I think first of all, let's see. So R cross S. Yeah. So in the 2D case, we have cross products, and it's confused when you pull out the T and U cards. Okay, yeah. So what T does is it scales this line here. So why don't we actually visualize it? Since we have Dragon Ruby, it should be pretty easy to visualize. So let's see. We'll just do display lines args, and we'll delete that in a sec. So display lines args. And so we'll just have our P equals vec2.new, and we'll put this at 400, 400. And we'll have an R equal to vec2.new, and we'll make this line 200 by 150, for example. And so why don't we first kind of look at that, and then we'll also add a T of 1. So we have our args.outputs, and we'll add a line, since I learned a new trick today. So we'll do p.x, and our y is p.y, right? And so this is our p position here. And the place that we're trying to get to is p plus r dot x, and our y2 is p plus r dot y, right? And so now if we do that, we have this line here. We'll put into this some labels so that we can actually see what's going on. P.x, y, p.y, and we'll have our text be p. And we'll also add in p plus r dot x, and I know I could have just put this into a variable, but that's fine. Y text, and this is p plus r, right? So we have this to here. Does that make sense? So now we can add in another line, which is our scalar. So p dot x, y, p dot y, x2 is p plus t times. So I'm going to actually have this in the opposite direction just because of the way my library is set up right now. But r times t gives us this value here, and we'll do y2 p plus r times t dot y. And this first bit will be text on, well, I guess we don't need this one here. We only need the second one. And what this is our text is p plus t times r. And it doesn't like that because I did something dumb, like not put a comma here. And now it still doesn't like me. Oh, I didn't add a comma here either. Of course. Okay, so right now they're overlapped. That's okay. So what happens if we set this to 0.5? Our TR moved to that position there, which maybe I should have put a solid there. Why don't we set the color of this to something else? So you can see now that's horribly difficult to see. Okay, so we have our line. Oh, no, you're not seeing an output. That's useless. Okay. Yeah, now you should be able to see DR. Can you see that? Okay. So this should catch up in a second. Well, I guess it's probably already caught up by the time I'm speaking here. So if we set this to 0.5, we set t to 0.5 in this case, right? Then we have a point here. If we set t to 1, then we're at this point here. If we set to 0, we're at this point here. And we set to 1.5, we're all the way out here. So these are all the different positions that we're looking at here. And so that's essentially how this works here. That's how the P works. Now let's do the same thing for Q and S. So I'm just gonna take this. Since you output TR-vec later, I only see blue. Yes, that is true. That is true. And I will actually fix that in a sec. Let me just quickly change this to also have P dot will do Q G Q dot and percent S. We'll do space. Something like that. And then this should be Q. And then we can do the same thing with our R and S. And we'll just have to switch a couple of these. I guess I could have just done the refactor tool, but sometimes I do things the hard, annoying way. Okay, that is not happy because those do not exist, so we'll comment these out for now. Let me actually add in some solids here so you can see what's going on. args.outputs.solids, and we will add in x or y with, so we'll do -3 width of 6 and a height of 6. And that gives us this point here. And then we'll also do the same thing for, man, I wish I put these into variables. That's okay. P plus r dot y. Right, so that gives us those two. So that's our original line. And then we'll do the same thing for the blue. So we don't need this one here, but what we do need is r times t times t. And we'll just set this blue to be the same color there. So you can see as we scale t, we end up moving it. Like right now it's half the distance. Now it's, if I set this to 0.75, it's 3/4 of the distance, right? So it's just linearly scaling along this vector. And then we can do the same thing to our q, which is gonna, yeah. we'll set our hue equals vec2.new on, we'll do 600, 300. And I'm not sure if this is going to intersect, but we'll take a guess. We'll do 200 there. And now we have this line here, and that does intersect. Great. And I guess we're scaling by t right now, which is not what we want to be scaling by. So we want to be scaling by a u. And now what's cool is if we want to find this point, which we will do, set that to green. Oh no, I hate that color. It's so hard to read, hard to see. Okay, so maybe that green is a little bit better. Yep. Cool. So now, essentially, we scale both of these things to try to get it to that same point. So we're essentially just adjusting our S and U values to hit that point. Does that make sense? And so that's what the T and the U do. And we just scale these things. And if it's greater than 0, or if it's greater than 1, then it's outside of this line segment. So it doesn't intersect as a result. And hopefully that makes sense. So now we can actually compute this stuff. So why don't we go back to our collision here, compute intersect, and I'll just make a note here that it's taken from, well, right there. Okay, so now we know where we got it. So we have our, yeah, it's a little bit counterintuitive at first, but it, as you work with it, it starts to make more sense. Great, yeah. So that's the goal here. So now all we're doing is we're computing we're just solving for the t and the u, right? And so that's what these little pieces do. Cross R. Wait, something's wrong here. There we go. Okay, over R dot cross on S. Did I do that right? R cross S, we divide both, Q minus P, and then we just start multiplying by that. Okay, yeah, that looks correct. Okay, so let's do cross product now. So we have our cross, which is our other vector that we're multiplying by. So all we're doing is we're doing vec2.new, and we'll do at x. So a cross product in 2D can be defined pretty simply as, so in 2D, we have v1 cross v2 equals v1x times v1 or v2y minus v1y times v2x. So this is our cross product in 2D. And then our dot product is defined as, this is kind of the easier one, right? Where you just sum up the element y's. So that's actually super easy to implement using like arrays and things as well in Ruby. Right? So those are dot and cross products. Maybe that's legible. It should be legible. Great. And of course, I make it disappear. So we'll just do, oh, sorry, this is not a vector. This is a scalar value. So we will do at x times v dot y minus at y times v dot x. And that gives us our cross product, and we'll do a dot product. I know I'm explicitly writing the returns here when I don't need to, but that's what happens when you have been programming in C++ for I don't know how long. Yeah, 15 plus years, I guess. So anyway, that should work. Now let's actually run compute intersect on. Okay, so now we actually have to do our intersections. So let's kind of go back to our original equations here. If I can find them. Kind of just splayed all these things around here. Okay. Why don't we look at the this instead? The source truth. Okay, so like we said earlier, if they're collinear, I'm just going to treat them as no intersection. So if r dot cross s equals 0, and okay, hello. So basically, at this point, we have just implemented rocket ship that flies around, uses a point mass, and has velocities. And we have just gone through the math behind the vector version of the intersection between two line segments. So we just kind of went through the full explanation of how that works from a mathematical standpoint. And sort of the logic behind that. So that's what this is here. So we have our scalars, and we're just basically multiplying things around to try to shift things. And yeah, there will be documents about that later that you can look at. But anyway, so back to kind of implementing this. So we also have our q minus p cross r. So we have q minus p dot cross r. Then that we're just going to return as nil. And we'll just, I guess that's what we'll do for no intersection. Else if, what condition are we looking at now? So basically, actually, I think in our case, we can just simplify this down to if r cross s is 0, we will return nil. So that kind of combines case 1 and case 2 here. So case 3 is where is the interesting one. So cross, and we don't need to check for this because we've already checked for that. So if t is less than 1 and t is greater than 0, we'll flip that around. Less than 1. And I know, then we can also say if u is greater than 0 and u is less than 1, then we want to return our coordinates, which are defined by, as we mentioned before, this ends up being defined as p plus t times r. And because it's the same point, it doesn't matter which one you use. So t let's see, P plus R times T. Else, and then I guess we'll, the other condition is that it's outside of this range. So I guess we'll also return nil in this case. So we can actually change this into r dot cross of s does not equal to 0 and this, and we'll change this to if this is the case, we'll return this, otherwise we'll return null. And so now, presumably, if we did things correctly, which I think we're okay, r.cross, we will at least try running this on our vectors here. So we have our ugly display lines function here, and we'll just do compute intersect on P, R, Q, and S. Intersection equals that. And why don't we just do args.outputs.labels, and we'll just initially just print this out somewhere. We'll just print it out to 100, 100. And we will set our text to be equal to our intersection. And what we can do is, I believe this returns does not return a vector. It might not compute. No, it should. Okay. So we can do a 2s. So this will return this as a string. So we'll do at x, at y. And now we have our intersection point. And actually, I want this to be a little bit easier to read. So we'll do I'm only seem to be returning one thing. So P is a vector, right? And so is R. So these are actually 1 by 2. So these are actually this whole thing is a vector. So that's why we get an output like this. Yeah. I don't know if that's clear. Can you read that? It might not be that legible, but we end up getting a vector like this. Yep. Okay, so now we have this intersection point, presumably. Let's actually make sure this looks correct in terms of the point. So we'll just output this. Outputs.solids. X on intersection dot x, y intersection dot y, and we'll do -3. I know there's like the sprite classes, which probably should be taking advantage of, but we don't need to be right now. Okay, so you'll notice why don't we make that red so it's clearer, but 255. Now we've computed the intersection here. That's pretty cool. So now if we have a plane, we can compute where it intersects. And we'll also compute intersections for the flight, I guess. Let's do that. Okay, so now we've made this display lines function. I'm just going to drop this into our org mode here, just for begin source, Ruby, something's missing here. In source, oh, maybe I just need an end source. We'll just pop that in there, and then we'll also add in, where's the intersection stuff? Compute intersect. Let's drop this in here. Oh, no, wrong place. Down here. And the nice thing about this is it'll get rendered nicely on GitHub, so I think. I'm assuming. So we can at least, then we'll have this as a reference later. Cool. Okay, so now we have our intersection point, and now as we're driving around, we want to, let's say, compute our intersection between this and a polygon. So why don't we create a polygon class, which all it's going to be is an array of points, and then we'll have like a little display function where we just have the lines around it. So I'm going to get rid of this thing since I figure we don't need it. Sort of clean that up a little bit. Have it elsewhere anyway. So below here, we will add a polygons class polygon, and we'll just initialize this as x, or why don't we just have our points, something like that, and we'll do that. And if it's nil, it's nil. I think that's allowed. And then we'll have an accessor on points. And let's see. Okay, so we'll add an add point. Point, and we'll just have at points.append, and these we'll assume are all vectors. So if point is a vec2, well, unless point is a vec2, we will return okay. And so if that's not a vec2, it will raise an error. Otherwise, we'll just add that point. And then we can also compute a collision for some line. So we'll have a point, and then we'll have a vector that's from that point. So that's basically our q comma s. And then for this, we'll just check. I think what we can do is at points.any do, does that sound right? Or actually, no, wait, at points dot each cons sound right? So this is polygon point 1, polygon point 2, and we're just going to compute this by doing, so this right here is our p-value equals that. Our q is our point. Or no, I'm sorry, this is our r. P equals 0.1. And I'm just writing this out explicitly more to be consistent with this, the Stack Overflow post than anything. But, and we'll just set this equal to vec. Then when we can compute intersect, and then I think what we need is, yeah. Yep, it will. And so actually one approach that we could take here, if we didn't want to, yeah, we'll probably just write the last pair separately. Or what we can do is we can do .zip on an @points.rotate one, which will actually give us the same thing. I think we can leave it at that, which obviously not the most performant thing in the world, but it's a decent way of doing it, I think. If this we want to return, I think I can just do return if that, and otherwise we just go on. So let's actually see if we can do that. So we'll add a little check collision. Def test check collision on polygon, or we'll just call this args, and then we'll just create a little polygon here. So we'll polygon.new, poly equals polygon.new, and then we'll just do poly.addPoint, vec.to, new, do 300, 300, and we'll add a few more points. We'll just make this little triangle here. 500 and 300, 400 and 600. And then we will also add a little display. Display args. And we'll just do the same thing here, where we'll rotate 1, do polygon point. We can just call those P1, P2, but that's okay. And then we'll do args dot lines dot or args dot outputs dot lines x pp1 dot x, y is pp1 dot y, and then width is pp2 minus, or I'm sorry, x2 is pp2 dot x and y2 is pp2 dot y. And now if we call poly.display, and then we will call test check collision on args, then it will presumably no longer, well, no, it will give us an error because, of course, I messed something up here. Pretty obvious, probably. 150? Oh, I guess we need something there. I guess we can, by default, set this equal to nil. At points or something like that. Does that work? No, it does not work. Why does that not work? Or nil. Wrong number. Oh, display. Wrong number for display. Okay, that would do it. Args. And we still have an error. Good. 141. So 141 at points.zip. Not rotate. What is it? Shift. Ruby array. I thought there was something like this. Flatten. Rotate. It is rotate. Why doesn't it like rotate? Oh, no. That would do it. Of course. Okay. Yeah, okay, so there's our little polygon. And then we'll just try to compute the collision with this P here. I thought we got rid of this rendering. Oh. Because... Yep, it's no longer nil. We should be okay. So let's now test this with collision. So poly.check collision on do vec.new, and we'll put this at 200, 400, and vec2.new, and we'll have this be 200 by 100, or yeah, just something like that. And actually, you know what? I think what we want instead of just checking for a single collision, we want to get all the collisions. So we will do dot collect on this, and we'll do next compute intersect, and if it's nil, we will there's I think something called reduce. Does that sound right? There should be not reduce. Do you remember what it was called? D compact. Yeah, so this basically gets rid of all the nil values here. So we can just use that. And I have something called vec.new, which is incorrect. vec2.new. And then 156, I do the wrong number of arguments. Arguments 2, 4, 3. Check collision. Why do I pass in args here? We don't need args. So now this, of course, doesn't give us anything useful because we haven't even drawn anything yet. So collisions. And then we'll just do solids X on, we have this hard coded in, so we don't really care too much about how we do this, I guess. But 397 width of 6, height of 6. Yeah, I only have. Fortunately, it's a Sunday, but I have a meeting tonight, so that should be fun. Okay, so that's that point. Okay, we'll just push this over here. That's better. Okay. So this should be 200 plus 300 minus 3. Sort of just a little bit of demonstration here. Our code, I guess, to just test it. Width of 6, height of 6. And then we will close that off. Outputs dot lines. And then we will just create a line there as well. 200, y is 400. And honestly, I should have just set these as a variable, but that's okay. We won't be doing too much with it. X2, 200 plus 300. Y2 is 400 plus 100. And now we have our line. And let's also get our collisions. Each do point and args.outputs.solids. My least favorite one is, I think, bounds, which I always think is borders, and it just bothers me every time. Mostly because I figure I should get it by now, since I use, as you know, I just basically do render targets and just direct primitive outputs constantly rather than doing what you're supposed to do, which is using sprites. But I guess render targets are no worse than sprites, so that's fine. Solids width of 6, height of 6, and we'll make this red. And there's an undefined method collision for main collisions. And now we have our intersection points, right? So that's kind of nice. And so now, why don't we compute our intersections? So we'll now check to see when this thing actually collides, right? So I'm going to plop this also into our org. Begin source and source. Yeah, render targets are great. I am obsessed with render targets since, or is it borders? It's either borders or, yeah, I guess it's borders, and I just keep calling it bounds because That's what I do. Okay, yeah. Now let's actually compute the collision between this thing and our triangle here, or whatever polygon. So we can add a new setup here. So for now, we're just going to create a very simple world where we just have polygon.new, and we will have our points vec2.new. And why don't we just use the exact same thing that we used here? So we'll just do, oh no. Okay, just do our roll, and then I think we can just delete that, and then I'm just gonna shift that up here, and I guess we'll just, yeah, that'll be better. Okay, that's fine. Does it not like this? Syntax error. Oh, commas. Commas, the thing I always seem to forget. Okay, and then we will, when we do our display, we'll also do args.state.polygons each, and then we'll do e.display. And, you know, at some point, maybe next video, I'll talk about filling it in using render targets. But for now, this should do. And now I bet if we remove this guy, it should, in theory. Yep. So we have now that triangle there. And so, let's see. We have our text display. Now let's also compute our collisions. So we have our update state. And for now, what we're going to do, obviously this is not, again, there are a lot of different ways of making this more performant. You know, you can use BVH trees, or you can use occ trees, or, you know, there are just a bunch of different ways where you can organize this thing. I think, yeah, to organize this thing so that you can just basically only look at collisions that, or just reduce the number of collision checks that you make. I'm not going to do anything. I'm just going to check against all of the polygons just so that we can get something up and running. So args.state.polygons. Each do polygon, and polygon dot check collision with our args.state.spaceship.position. And actually our velocity vector here is, why don't we call this our difference in position equals args.state.spaceship.vel times dt. And position. And we'll add this kind of at the end after all this stuff, just to sort of simplify things a little bit. So we'll do a collision check on that and our difference in position. We can certainly do it. I'm actually not sure if I'll have the time today, just because I have a meeting today, this evening in a couple hours, but I will need to do a little bit of prep for. And probably want to eat dinner before that or something. We'll see. But anyway, so we have this. We've done our collision check here. And why don't we just render collisions equals this. Collisions dot, and actually for now, why don't we multiply this by some large number? times 100, and then we'll see when we're close. Collisions dot each do point, and args dot outputs dot solids. We'll do point dot x minus 6 or 3, point dot y minus 3, and we'll have a width and a height of 6 each. And we'll just set this red to be 255. And now the idea is at least, yeah, so you can see we can compute, when we're driving in a certain direction, we can compute our intersection of the heading. Why didn't it show up there? Should have shown up. Does it only work in this direction? Or is it that it's, oh, you know what? We're going over. So we actually need to apply our position here. Position. We'll just create a new vector on this args.state.spaceship.position 1280 .x args.state.spaceship.position.y. Okay, so now presumably if we go through and keep going, we will, yeah, you can see now when we collide, we have that information there. Okay, so now that we have that, why don't we check for when it actually goes through? So collisions happen basically when this thing returns something. So right now, if we're just driving along, you'll notice it'll just flicker for a second there. It's probably not even visible on YouTube. But we just have the collision just flicker for a second, and then that tells us, okay, we've collided with something. So we now want to define our volumes, because if you recall, we are trying to do refraction. And so we'll call this just a polygon. Yeah. Right? Yeah, so we have all sorts of fun things going on now. So we have polygon, and we'll have access, attribute accessor on polygon. And then the other one that we want is actually our index of refraction, IOR. And so essentially what we're going to be implementing here is something called Snell's law. And Snell's law is the equation which defines how two vectors, or how light will be impacted by refraction. So I think essentially what it is we have our piece of glass, and inside of this is one material, and outside is a different material, and we have some piece of light that's coming in here, and it goes in at some theta, so this we'll call theta 1, and it leaves at a different theta. So this is our theta 2, right? And so there's a relationship there that we can define, and that is using this thing called Snell's. Oh, you probably couldn't even see that. we have two thetas. So we have we go in at one angle and we come out at another. And that's the thing that defines that is called Snell's law. And very simple, we have our input theta, where our output theta, the sine of it, over the, yep, I need to get better at that. This is why it's only the first stream, right? So theta 2 over theta 1 gives us, or sine of theta 2 over sine of theta 1 equals the ratio of our normals, or our IORs. So our index of refraction for part of one side, well, yeah, so it's sine of theta 2 times n2, which is our index of refraction on this side, equals our n1 times sine of theta 1. So that's nice, except for then we'd have to figure out all these angles, which is annoying. So we will take a different approach instead. So we can actually look at, there's a vector variation of this, vector form, which is just defined by, you take basically this trig function and you spit it, feed it in here and it spits out this equation here, where R equals the fraction between the ratio of the IORs, and C equals the, I think n is defined as the normal vector? No. Then n points to the side without the light. So it's the side that we're coming from, the normalized plane normal vector n. So we're basically looking at this vector here. And it should, towards the surface side where the light is coming from. Yeah, so I think this is the normal vector in this direction. So step 1 is to compute the normal vector, and then from that we can, yeah, it's not the most efficient way of doing it. If you want efficiency, then you should be doing just the direct sine and arc sine, presumably. But, I kind of like keeping things in vector form just from a mathematical standpoint. So we can kind of take that approach and go from there. Oh, hi. Yeah, no, I think we've been going strong so far. So, but it's been, so right now we have a little spaceship that we can drive around, and we can also compute collisions between polygons and our spaceship. But of course, it doesn't do anything. The one thing is that, we're, again, not dealing with anything with like performance right here. So if we want to just use if we want to do it kind of as a performance, want to do it in a performant way, we should be taking the sines. But here we are. So, Vermont, let's see, vector form. We'll just take this. So this is a refraction. And we could potentially compute a lot of this using a dot product, but okay. Let's get started. So we have, okay, so the very first thing we're going to do is we're going to try to compute the normals of our lines. So normals can be computed very simply. So for each line, we can define that as, if we have some line here, and we have this be, let's say we can call this, won't we, for simplicity's sake, we'll do it this way. So we have this is P, and this is P plus R, right? Then in this case, our normal direction can be defined as, well, we have our Rx and our Ry direction. Instead, what we want to do is negate one of these. So there are two normals. There's this one, and there's this one. And these two will point in this way and this way. I guess the first one is this one, and the second one is this one. So why don't we actually first just check that out, since that is pretty simple to test. Right, so for each of our polygon points, polygon.new, so we have our volume, let's see, where's our class polygon? And we will, why don't we have a display def display debug, and we'll do, and again, not performant, but yeah, we did cover a bunch of things. So if you want to watch it from the start, you're welcome to. We spent a lot of time, I think, on basically how the vector form of the collision equations work, or the intersection equations work, and that hopefully is clear, but that's, yeah, probably for now, just staying online is fine. I don't do anything too complicated throughout the whole thing, so yeah, right? But of course I talk slowly, so you could probably put it on like 4x speed and be fine. So we'll do our normals. Normal equals 0.2, or why don't we say our difference in points equals 0.2 minus 0.1, and our normal ends up becoming norm equals vec2.new on d.y, and we'll just negate that, and d.x. And so that's our new normal vector, and we can just do x d point, or I guess this 0.1 dot. Okay, we'll actually have an average of this too. So center point equals 0.1 plus 0.2, and then we will divide by 2. And obviously that'll error out. That's a good thing, right? If you didn't notice it's been 2 hours, since that means it hasn't been totally boring. I think you've been paying a lot of attention too, which, at least from here, it feels that way. X, y, center point dot y, and x2 is now our center point dot x plus norm dot x, or norm is a bad term. We'll do normal. The reason I don't like norm is, of course, norm is the absolute value of a vector, so normal dot y. And I messed something up here. There's a comma missing. I always mess up the commas. Okay, so now we also call display debug up here. Polygons.each, polygons.each. Okay, we'll do p.display debug args. And it doesn't like this. Division doesn't exist on this yet. Okay, we will implement that. And I think so far I've been defining these operations as element-wise. So something kind of like that. Let's see. That looks better. Okay. So now, presumably, we have that defined, and we have now our normal vectors there. They're kind of large, so I will add a magnitude to our vector. Def mag, return path square root on at x times at x plus at y times at y. And that gives us our magnitude. And then we will just divide. Good. Good. I'm glad it's been interesting. So in our display debug, we'll just divide our normal to make it normalized. And we'll probably just multiply this by 10 or something, so it's at least visible. 10 times. And now we have our normals. Does that, am I even displaying that? Yeah, I am. Okay, good. I just needed to make sure. It's half the time I find I'm not displaying anything that I intend to. G is not working. Why aren't you working? Am I doing something wrong here? Is this still, it's still rendering. Why is this not showing up? Maybe it's, oh, it just wasn't read enough. Okay. Okay. So now we have our normal vectors, which is useful, but our normal vectors are only useful if we have somewhere that we use them. So let's look at so we have our render spaceship. And for each of our polygons, we currently show where the collisions are. And I think earlier we did something where we just multiplied this by 100 to make the collisions go further. And so we'll show the normals at that position from the direction that I keep almost saying robot, from the spaceship. Too much time with robots. Okay. So we compute here the norms for each of these by looking at the particular polygon or the particular segment that we're colliding with. So the way we will do that is presumably, I guess we can return along with this our points. So I'm not sure I love this, but I guess it will work. So next on, does this make sense? Compute intersect. Intersect equals that. And if intersect dot nil, we'll do unless. And we will just do next on intersect comma, what am I missing here? P1 comma P2, and this, I don't know why I wrote it that way. P1 comma P2. So this is our line. And now everything will break because our intersect check collision does not give us what we expect. So collisions we'll do point and then line And maybe go check. Check collisions. So point line. Did I feel like I missed something here. Collisions. Okay. Yep. Point, comma, line. And then we'll do that. So now we presumably return that, which we haven't actually used yet, so we don't see anything here. But does anyone know why, by the way, when I'm not in this window, it becomes really choppy? I think it's because it's not, not focused, so it just tries not to re-render as much, but it's kind of annoying. Like when I click on it, it becomes smooth, but otherwise it just kind of jumps, so. Process, okay. So we have our process input, update state, and we now want to probably just render our normal lines. So we have our collisions.each, and we have our line as well. Outputs.lines, or .lines, and we will add in. So first thing we will do is we'll do from our collision point. So x point.x, y point.y, and then our x2 on, let's see, so we now have our normal equals line 1 minus line 2 is our diff points, and our normal is equal to vec2.new on diff points.y and diff points.x. And so now we can do normal plus, or point plus normal dot x, and x y2 is point plus normal dot y, and we'll actually divide this by the magnitude of diff points. Divide by diff points dot mag. I see. Yeah, unfocused. I guess it probably was patched, since I presume it's not using as much as my resources now. It doesn't seem to be rendering every step, so good. So points, normal, and we'll also just multiply this by some value. We'll do times 10, or times 20 maybe, times 20, and that will give us, maybe that will give us what we want. Let's see. Well, no, that did not like that. Non-float value. Normal update state 60. Diff points dot magnitude. Oh wait, why am I doing? Wow, I tried to one index that. That's pretty bad. I don't know when I've ever tried to do that. Yeah, okay, so now you can see we have the normal points for that. But one thing that you'll notice is it doesn't really matter which way we come from, it will show the normals on the same side. And so even if we come from that side or come from this side, the normals show on the same side. We want the normals to be facing the direction that we're coming from. So the way we do that is we currently have our normal, and we also have the direction vector, or the difference in position here, and we can take the, I think earlier I mentioned the dot product, and how dot products are basically the magnitude times the cosine of the difference in the angles, right? So what that means is if it's greater than, if v1 dot v2 is less than 0, then the angle is greater than 90 degrees, and if the absolute value of it, and if this is, wow, v1.v2 is greater than 0, then we can say it's a small angle. You're gonna rewatch this? It's already been several hours. That's a long time. But okay, I appreciate it if it's interesting. That's good. Okay, so that gives us, so basically all we're looking for is the case where if we have our spaceship and it's going towards the line and we have our normal vector, we're looking for the case where this dot this is, I think we want it to be negative, and that will give us a value that, that'll give us the correct direction. Let's test that. Okay. Deposition. So normal. Outputs dot lines. Let's see. Okay. So our diff points, we have our normal, and we'll also do v1 or normal dot, and then we'll do our difference in position. And if this is less than 0, then we will instead normal equals, let me see, that is less than 0, then, oh wait, no, I'm sorry, is that what we want? That is less than 0, then we are presumably facing the correct direction. And otherwise, so if this is actually greater than 0, what we want is we want normal to be equal to, yeah, this is not exactly what we want, but just basically for the point of normal. Just, hard to get something to work for now. Okay, so now we have end here. Let's get rid of that. And presumably now, I think we can render this with a different color, maybe? Or no, I guess that should be correct now. So when we come from this side, oh, wait, something's wrong there. Oh, normal.y, that would do it. Diff points.y. Okay, so now, presumably, if we come from this side, our normals all point in the direction that our spaceship is coming from. Does that make sense? So we always know, okay, we're coming from the outside right now we're in the inside. And so that lets us do a lot of things that are kind of cool. So that kind of lets us check to see which side the collision is from. And that also helps us with our refraction, because now we can apply Snell's law, which, if you recall, is this guy, and is also, there's a vector form which relies on the normal. So this is the simplified version, so to speak. So we'll have our refraction args, and we will have our normal vector, and we will have our, let's see, refraction angle. So input angle, we'll just call it that. I think which is actually L, right? Yeah, given a normalized. So we'll just call it L to be consistent with the literature. And we'll, or like vector, yeah. Input vector is fine. And then, what am I missing here? N1 and N2. And am I missing anything else? Input vector, the normal, N1, N2. Okay, cool. I think that's everything. So let's first compute our R and RC. So this is N1 over N2. And C equals negative on of the normal. So because of the way my thing is set up, I end up having to do that, but that's okay. And then we will just do this dot, and this is our input vector, which is our light vector here. Okay. And we will return R times, well, okay. I really need to figure out how to set this up a little bit better. But input vec, or I guess L dot L equals input vec. Just to be consistent here. I guess this just has to be times R since R is a scalar. And then we can have R times C minus math on square root of 1 minus R times R. And I know in game world we hate square roots, but I don't know, in robot world we use them a lot, so. And then we'll multiply this by our normal vector. Normal times that. So this bit here is a scalar. This is a vector, and this thing is a vector, so in the end we get a vector output. Okay, so now why don't we also display our refraction angle? So for each of these, we will show args.outputs.lines, x point.x, y point.y, x2. Yeah, well, you know what I mean. It's definitely a performance hog, but I think like most of the things that we are doing, at least most of the things that I do, don't really need to be that fast. So I figure step 1, get things running, and then step 2, clean up the parts that need to be. Yeah, it's always, pre-optimization is never great, right? So you just do some profiling after the fact and you try to figure this stuff out, which I've done a lot of. So I used to write Oh, interesting. So you tried the vector normalization versus square root. Yeah, or the and square root versus the trig, and the square root was faster. I guess I'm not that surprised. I was kind of interested in that comparison, but because trig operations are expensive too. So, and this only has one square root and a couple multiplications. While I think the trig there's inverse, there's the sine, and then there's the arc sine. So it ends up being a little bit more expensive that way. So we have our d position. So it's our difference in position, which is our input vector. And then our normal is just our normal. And then for now, we'll just always have the same index of refractions. So we'll just be we'll be turning every time. So IOR, typical, I think IOR, I think water was 1.3 or something, and there's like 1. So we'll just pretend that this is a reasonable value. And we'll do point.x plus ref.x, and xy2 is point.y plus ref.y. And presumably that will give us something, which is good, but we will see. Okay. So now as we kind of drive along here, then we may see a tiny little thing. So we'll multiply that by some large number, 30 times that, so that we can actually see the thing. Okay. I'm actually gonna switch this over to, yeah. So you can see now we're looking at these are supposedly are we looking at the right values here? It's hard to say, actually. Maybe we'll change the IOR 1.3 to like something drastic. Also, one thing is right now I have the GTK reset up here. Let's not do that, and instead we can have this in process inputs to say args dot if args dot inputs dot keyboard dot down or dot backspace dot down. Let's see, key down dot backspace. Key down dot backspace. Then we'll call gtk dot reset. And that way, usually it'll just go, and then if I hit backspace, it will reload. Did it reload? I guess. Why are you erroring? Non-float value. Oh, if key down dot backspace, I figure it must be here, right? No, 47. First time we go around, the orient doesn't exist, I guess. Orient is 0. No, that's right. That looks correct to me. Okay, why don't we just try every once in a while I end up having to reset this. Yeah, vector normalization, I just use divide by magnitude. That seems to work for me, at least. Oh, okay. Why don't we also... Why is this not working? I thought that's what I usually do. GTK reset. If args inputs keyboard key down backspace GTK reset. It's good enough. So at least now we can sort of interact with it a little bit better. So as we kind of drive around, okay, maybe that's working. What is going on here? Refract. Points dot refraction. Ref divide by equals ref dot mag to normalize it. I'm actually not convinced that this is working correctly. It doesn't really look like it. Does it? Does it look correct to you? Refraction. Let's see. Let's take a look at the math again. All right, maybe we can try flipping the N1 and N2 and seeing how that impacts it, since that, of course, should impact it. It just kind of looks like the normal vectors, you know? So I think there's something wrong here. Refraction. We'll do the vector form. L is equal to, so R is equal to N1 over N2. See that? Yeah, I have a square root inside of my magnitude method, at least. If you, my magnitude is just square root on the X and Y, but there might be a better way of doing that. I think the other way of doing it is you take the, yeah, you can take the dot product and divide that by the cosine of the angle, or the, yeah, and that should also do it. So update state, refraction, okay. So we have our refraction is equal to R times L plus the normal vector times, oh, you know what? This should be normalized, shouldn't it? Normal equals, divide by equals normal dot magnitude, and maybe that'll fix it. Oh, and maybe also our L. Is that the case? L, normalized light vector. Yeah, okay, so that'll do it. Dot magnitude. Okay, so now presumably it'll look a little bit better. That does not look better, does it? Okay, L equals that, normal times, yeah, I'm sorry, this has been taking way longer than it should. L times R plus R times C minus the square root of 1 minus R times R times 1 minus C times the normal vector. Okay, I guess I will assume that's right, even though it kind of looks not so convincing. Okay, well, presumably it's right. It could also just be a rendering issue here. Point.x, it should be the purple one, which I think should be being rendered correctly. Yeah, so that's being rendered correctly. Then we have our normal. Okay, let's reset that. It looks almost like it's just scaling on that normal, which isn't what we want. Well, right now I have the IOR set to, yeah, I thought that too. So I set the IOR to 30 here for one side. So it should have been enough. Of course. Our square root domain. Why would it be out of range? 88. For some reason now our C is equal to normal times the dot of L, which should be fine, I would have thought. what happens if we flip this again? Does it? Yeah, it's happy then. So for some reason, when it's opposite, it's unhappy. I think because the C value becomes, or I guess the R becomes too big. And when the R is too big, then it becomes negative. Which, oh, I guess the issue is that when it becomes negative, then it can only happen. Yeah, that's total internal reflection. So essentially, if that happens, we're looking at reflection instead of refraction. So it should presumably bounce off in that case, but we won't worry about that for now, especially given the time. So we'll try to put something like that, maybe. No, it still doesn't like that. Okay. Does it not like any value where this is smaller? I guess not. But it's kind of strange because I thought we handled. Oh, I guess it's more to do with the angle that we were going at than anything. So I bet if we're just kind of going like this, if we set this to some large value, it should be okay. Yeah. So it's basically, if we just go at an extreme angle, it's unhappy, which is hard to recreate because I am terrible at flying this thing. I should, yeah. So basically, extreme angle results um, in total internal reflection, which we can also add in, I guess. Why not, right? Refraction. So if, so this is the radicand equals 1 minus r times 1 minus c times c. If radicand is less than 0, then we return, and I think the total internal reflection is just that the, let's see, total internal reflection. Let's take a look at the equation here. So critical angle, total internal reflection. We can totally handle this. This is not the worst case that we ever hit. Total internal reflection. Yeah. Right. See, glass surface. Incident rays being split, partially refracted, reflected. The critical angle is the angle in which it switches over. This is refraction, and we end up with something called total internal reflection. And I feel like total internal reflection is actually feels like it should always be the same angle, but I guess it's not. Obviously, refraction cannot exceed 90. For electromagnetic waves, so total internal reflection is where basically with light we have a couple different cases when light bounces. And so case number one is we have our surface and we have light coming in from some angle and it refracts, so we end up coming out at a different angle, right? Total internal reflection is where the angle is steep enough and this n2 is large enough compared to n1 that it reflects completely. So you see this very often in the case of what are those called? Fiber optics, right? So fiber optic cables, basically what's going on is you have your cable, which I will draw in not the color of our light. And we basically just have this bounce back and forth. And this is called total internal reflection. And if this angle is sharp enough, then presumably when it gets to here, it can just kind of poke out. So this is total internal reflection here. I don't know, actually. I was debating about it. Versus this is refraction. I don't know if I want that behavior in the game, to be honest with you. For now, I guess we can just return whatever the input vector is. And that way we'll just say, hey, if it's a steep enough angle, then it won't impact it, which seems wrong, but we'll just do that for now. And that way at least we'll have something. Let's see. So I guess the easy way of testing this is by making this a lot smaller than the other one, right? And that presumably will give me something that's good enough for now, and then we can reevaluate that later. So now it's just basically taking whatever the input vector is, which, yeah. But yeah, basically I do want to implement that at some point, total internal reflection, and then that way, you basically can bounce around, and that should be an interesting piece. So, okay, anyway, let's adjust the velocity vector based on this. So, if we have a collision, total internal refraction, but swap the vector to the other side to convert it to refraction as well. Yeah, so I think basically it's the inverse on the refraction, right? So I think what we do is we can flip the n1 and the n2 and flip the normal, and presumably that will give us the value, maybe. It's something like that. And I'll look into that offline. I'll just look at the math a little bit, but I know I understand it before I try to implement it. But okay, so we have our refraction angle, and what we'll do. No, for breakout, actually, they do something pretty simple. All they take is they take the input angle, and this is just theta 1 equals theta 2, and that's all they're doing. So they have no impact on, the index of refraction actually doesn't make a difference. So yeah, that's kind of the big difference there. Well, in this case, we actually have different theta 1s and theta 2s. since we're dealing with different index of refractions on either side. So I think what their situation is they're assuming a frictionless wall that has what is that? It's a purely elastic collision, I think, or purely inelastic collision. I'm sorry. Yes, inelastic collisions are so elastic collision is if we have 1 and 2, and let's say we have 2 is not moving. When it collides, it ends up moving together like this. So this is a pure elastic collision, I think. Elastic. Stick. And pure inelastic is when this results in 2 going this way and 1 going the other way. So that's like a billiard ball. So there are kind of these 2 different cases where, basically this one is like if you took, I don't know, 2 like pieces of pudding or something and threw them at each other, then this is what you'll get. They like kind of merge together versus like billiards. This is what you have. The pure inelastic. Or I'm sorry, yes. Pudding, you have the pure elastic and pure inelastic for. I think that's right. Don't quote me on it, but it's like one of the 2. Okay, so why don't we actually adjust our motion here? So our D position, we've computed like this, and actually we can, instead of doing this, well, yeah, infinite mass on bricks. That's right. That's how you'd physically model it. Or you just kind of assume it's static. Otherwise, it's fixed to something that is infinite mass, right? So like in our case, when we throw a ball at the wall, the Earth is the whole. So the piece of wood, the wall is attached to the Earth, which basically, for our purposes, has infinite mass, which is why we don't see the wall and the whole Earth rotate around us, which would be pretty jarring if that didn't happen. So, and especially since the rotational inertia there, we have our, what is that? Our force times distance equals our, force times distance ends up, I think, equaling our torque. Is that right? Something like that. So that's essentially if we're really, really, really far away and we have a tiny force, then it ends up having basically 0 torque. So if distance is something's not right. But that equation I think looks right. So I don't know. Oh yeah. I mean the equation's right. It's just that there's so much angular momentum at that point. But Earth mass, is what we deal with. And actually more than that, in the case of rotation, it's the Earth rotational inertia, which if we talk about like moments, that basically we can model that as a circle or something, or sphere. And then that basically has a really, really large moment of inertia, rotational moment, which is basically like momentum, but for rotational elements. So anyway, and that's actually a big part of what I did for my drone simulation, which was sort of the moments on the drone itself. So that's actually modeled somewhat physically correctly, although there are some limitations there. Namely, I don't model the individual rotors, which you need if you want to do a proper drone simulation. That's absolutely necessary because there's rotation in the z direction. That's absolutely critical. But anyway, I digress. So let's set. Oh yeah, are there non-hard coded canvas dimensions? How do I is there like a canvas width, canvas height kind of thing? Because I asked about that at one point and all I was told was that it's 1280 by 720 and that's what I should do. So I hadn't worried about that. But anyway, I will let you get back to me on that. Let's see, difference in the points. So we now have our refraction direction. So refraction times. So I am just going to, for now, say that our dt is now, or our d position is equal to our refraction. I'm just going to pretend that I'm not going to bother to compute the exact collision point, I think, just because it becomes a little bit more tricky. Oh, args.grid.h. That's awesome. Okay, I did not know that. Today I learned. Again, brand new to Dragon Ruby, so that's fantastic. Okay, cool. So I should be able to do... Oh wait, do we not have that yet? Is that not a thing? args.grid.h, args.grid.w? No? Okay. Anyway, I will worry about that later. So we can look at dposition.magnitude, and that now gives us our new angle. So now presumably when we... Wow, this is not very exciting. I'm not sure why it's not refracting more. I presume it's because there's something wrong with my refraction code. Okay, why don't we slow it down a bit? And it certainly jumps. Oh, I should go the other way here. Oh, there we go. Yeah. So now we have refracting motion, which would make it pretty hard to drive. Yeah. Anyway, so I think that's basically the main stuff that I wanted to do today. If there are any questions about any of this? And if not, I will, I'm going to just kind of organize this into the org document. And I'll also just post what I have here in the GitHub. And so that, you can look at it for reference or whatever else you want to do with it later. And then there will presumably be a part 2 on this at some point. So oh, okay, so we do have args.grid.h. Okay, great. That's good news. I will also change that on mine. Okay, so I should be able to do args.grid.width and args.grid.h. And now, oh, look at that. Beautiful. Yeah, it works. Okay, so that's cool. Or I guess actually I have the modulo somewhere else as well. So let me fix that first. Yeah, that's kind of cool. Okay, so obviously we didn't get to everything that we wanted to get to, but I think that was a lot of fun. Thanks for joining. And next time, I guess we will try to do a little bit more with this, or maybe we'll do like the classic moon landing game where you have like a little spaceship and we apply the forces onto it, and that way we can talk about various torques. So yeah, so I think that would be cool. Yeah, so thanks for watching. All right, and I guess I will see you on the DRGTK Discord. All right.